All right, we are about to begin Ralston Valley High School Chemistry's AP lecture series, Chapter 4, Lecture Number 3. This lecture covers chemical reactions. In particular, we will focus on acid-base reactions. Let's go ahead and get started. So later on in second semester, we're going to do an entire unit on acid-base chemistry. So this particular set of notes is going to focus only on kind of basic introductory acid-base reaction mechanics and a little bit of information about titrations and stoichiometry as it relates to acid-base reactions. In the AP chemistry test, the most common definition of acid bases you're going to be using is the Bronsted-Lowry acid-base definition. Recall that acids and bases are defined in a variety of different ways, among them Lewis acids and bases, Bronsted-Lowry acids and bases, and Arrhenius acids and bases. Again, we're going to focus here on the Bronsted-Lowry definition, which defines acids as proton donors and bases as proton acceptors. And remember, as a synonym for a proton, we're going to be using that H-positive ion. Recall that hydrogen in its neutral state has one proton and one electron. So a H-positive ion has lost that electron, which really leaves behind only the proton present there. So a proton and an H-positive ion are really synonyms of one another. We'll use them interchangeably from here on out in the lecture. There are several different classifications of acids again, and one of the things we're going to be looking at is how many of those protons these acids can donate. An acid which can donate only one proton, or in solution which dissociates to only produce one H-positive ion, is referred to as a monoprotic acid. Mono being the prefix meaning one there, so one proton it can donate. As opposed to an acid which can dissociate to produce multiple hydrogen ions or donate multiple hydrogen ions in reaction. We refer to those as polyprotic acids. Classic example of a monoprotic acid, really familiar one, probably that you all know and love, is HCl, otherwise known as hydrochloric acid, which when it dissociates produces one H-positive ion as well as that Cl negative ion. And polyprotic acid you're all familiar with, something like sulfuric acid, which is H2SO4. That H2SO4 can dissociate into an H-positive ion and the bisulfate HSO4 negative ion. The bisulfate ion can also dissociate to produce H-positive and SO4 2 negative, the sulfate ion. So in its complete dissociation, sulfuric acid separates apart into two separate protons, meaning it is therefore a polyprotic acid. So let's go ahead and move on and look at some common acids you'll come across in your chemistry experience. One of the most important properties of acids and bases you need to be familiar with is whether the acid or base is referred to as a strong acid or a strong base, or conversely, if we are dealing with weak acids and weak bases. Strong and weak are not characteristics which refer to how dangerous the acids are. They really mean the degree to which these acids dissociate in aqueous solution. A strong acid will completely dissociate into ions at low concentrations in aqueous solution, whereas a weak acid or a weak base will only partly dissociate, and more of the acid molecules will stay together molecularly rather than dissociating. That is, those weak acids tend to exist in equilibrium with their dissociated ions in solution. So essentially, strong acids dissociate to completion, weak acids dissociate partly and exist in equilibrium with the ions in solution. It's very important. There's very few things the AP test is requiring you to memorize these days, but the list of strong acids and strong bases you'll commonly come across is one of those you need to know by heart. So let's just go ahead and list. You were introduced to these last year in our introduction to acids and bases. There are 7 strong acids I want you to be familiar with. 3 of those are binary acids, that is made up of hydrogen ions bonded to one of the halide anions. So we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. And then we've got 4 ternary acids, which are strong acids, those being sulfuric acid, H2SO4, nitric acid, HNO3, chloric acid, HClO3, and perchloric acid, HClO4. So those 7 strong acids will, at low concentrations, generally below around 1 molar or so, will completely disassociate into their ions in solution. On the other hand, we've got a series of strong bases I would also like you to be familiar with. These strong bases are easy to remember because all of them are metal hydroxides. In particular, any alkali metal hydroxide you come across is going to be a strong base. So we can list lithium hydroxide, sodium hydroxide, and potassium hydroxide. Rubidium hydroxide would certainly be a strong base as well, as would cesium hydroxide. But rubidium and cesium are so rare that we're never going to really encounter them in lab, so we're not going to worry about those in terms of ones we have to memorize or keep track of. We've also got some alkaline earth metal hydroxides to deal with as well, we consider to be strong bases. Barium hydroxide, calcium hydroxide, and strontium hydroxide would be 3 of the alkaline earth metal hydroxides that we would expect to be strong bases. And remember, those alkaline earth metals with a +2 charge as ions will therefore give our alkaline earth metal hydroxides a different formula than the alkali metal hydroxides. Let's see, for example, barium hydroxide again is a Ba2 positive ion, which when it combines with the OH negative ion will form BaOH2, the formula for barium hydroxide. So again, you don't have to memorize too many different things in AP chemistry, but one of them really is these strong acids and strong bases. So please do commit those to memory, and let's move on. So when acids and bases react together, they undergo a process we refer to as a neutralization reaction. And that neutralization reaction is really just a double replacement reaction, or we called these last year partner swap reactions, in which the cation from the acid gets together with the anion from the base and vice versa, and they essentially swap partners. And we've given you here a generic formula for a double replacement acid-base reaction here. We've got a generic acid HA. H again is the hydrogen cation, and the A there is the anion bonded to it. And then we've got our generic base there, BOH, we'll refer to that as our generic strong base. And when those react together, the H positive cation will get together with the OH negative anion, forming, not surprisingly, HOH, otherwise known as the very familiar H2O, water. And again, that's why we refer to this as an acid-base neutralization. The thing that makes an acid here, the H positive ion, gets together with the thing that makes a base, the hydroxide ion, and they form a species which we know to be neutral, that is the species of water. And then the second product of that acid-base neutralization reaction is that species there, Ba, which is what we refer to as a salt. A salt is the generic term for really any ionic product of the acid-base neutralization process. So for a classic example of one of these you all are familiar with here, let's just go ahead and real quickly here write and balance a molecular, ionic, and net ionic equation, which describes the reaction between hydrochloric acid and sodium hydroxide. So formulas first. We went over these on our last slide here since these are all strong species. Hydrochloric acid is HCl, and we're going to combine that together with our sodium hydroxide, NaOH. And if we have a look at the ions that are present here, we've got the H positive ion and the chloride Cl negative anion. And then our base here, the sodium ion Na positive, and the OH negative anion present there. And again, when we partner swap there, hydrogen ions get together with hydroxide anions, and we form water, H2O. And then we form the ionic salt, which is the second product of this neutralization reaction, which in this case is a very familiar salt, that is NaCl, otherwise known as table salt. So we've got a molecular equation right there, and happily for us, as we were going through and figuring out the charges on the ions to write our products here, we've also got a head start on writing our ionic reaction right here. Now, remember, in an ionic equation, we always are showing species which dissociate in solution as separated ions. Because the hydrochloric acid here is a strong acid, that means we would expect it to be dissociated in solution, and as such, I'm going to write that as H positive and Cl negative. Same applies to the sodium hydroxide here, which would yield Na positive ions and OH negative ions when that strong base dissociates in solution. And then on the product side, we've got NaCl, sodium chloride, which I happen to know is an alkali metal salt, which means, therefore, by our solubility rules we discussed earlier, we know this will be a soluble salt. So we're going to keep this thing disassociated as Na positive ions and Cl negative ions. And then the molecular species water, which is not going to dissociate to an appreciable degree, as again it is covalently bonded there. And so we'll leave that as H2O. And so we've got now here a happily balanced ionic equation. All that remains is to move on to write the net ionic equation. And as you recall from last year, to go from the ionic equation to the net ionic equation, the big step we need to take is to cancel out any spectator ions present. And you'll note here our spectator ions are those present in the salt. That is, we have sodium ions on both the left and right side. So just like a spectator, they're present but not participating in this reaction. So we can go ahead and cross off those sodium ions. And likewise, the chloride ion, Cl negative, is present both before and after this reaction occurs within the aqueous solution, which means we can cancel it out. It's not really participating either. And this yields our net ionic equation, which again shows me why we call this a neutralization reaction. We have H positive plus OH negative reacts to form H2O. And happily for us, as it turns out, that net ionic equation is the same net ionic equation for any strong acid, strong base titration that we will be dealing with, as long as we are looking at monoprotic acids. So we don't have to rewrite all of those processes along the way. We can use the net ionic equation as long as we recognize we're dealing with a strong acid, strong base reaction. We can just skip right to the end and recognize it's always going to be H positive plus OH negative makes H2O. So that is writing neutralization reactions. Now, on the previous slide, we had a look at an acid-base neutralization reaction where we used a strong acid and a strong base. On this slide, we're going to talk about what happens when one of those species is a weak species. Recall, a weak acid or base does not completely dissociate into its component ions within the aqueous solution. That is, it exists in equilibrium with those ions because the conjugate base species has a strong affinity for holding on to that hydrogen ion. And as such, we're going to write these reactions when we're dealing with weak species with two directional arrows here as we show their dissociation. As an example, we've written down here for you the dissociation of acetic acid, otherwise known as vinegar. That acetic acid, CH3CO2H, you see here, dissociates into hydrogen ions and acetate anions. But because that acetate ion itself is a fairly strong base, that is, acceptor of protons, this reaction can also effectively run backwards, and the CH3CO2 negative anion can pick up that hydrogen ion out of solution, reforming the molecular acid. So again, this is a system that will establish equilibrium, and for a weak acid or weak base, that equilibrium is going to lie to the left-hand side of this system, so on the reactant side. Now, even though this dissociation of these weak acids is not complete in solution, when we react weak acids with strong bases, those reactions we will still assume go to completion for the sake of our stoichiometry, because even though the acid itself present is weak, like for acetic acid, for instance, the hydroxide ion is a very strong base. In fact, it is the strongest base that can exist within an aqueous solution. And as such, it's got a super affinity for holding onto those hydrogen ions. It is much stronger of a base than the acetate anion. And so if we mix together acetic acid and sodium hydroxide, we can say, we're not going to write that as an equilibrium. We're still going to assume that reaction goes to completion due to the very strong nature of the hydroxide anion as a base. So with that in mind, let's do one more quick example here and write and balance molecular ionic and net ionic equations describing this time a reaction between acetic acid and sodium hydroxide. So for the molecular equation, we've got an easy relationship here. I've given you already above here the formula for acetic acid, CH3CO2H, and sodium hydroxide is familiar, NaOH. And again, we're going to react these things together. The acetic acid will donate its proton to the hydroxide anion, and will therefore form, again, not surprisingly, water. And the second product of that reaction is going to be sodium acetate, that is the salt we make out of the remaining ions present in our solution. Now, that molecular equation, happily for us, comes pre-balanced. Here's where I want you to be very, very careful, though. I want to go ahead now and write the ionic equation that is showing the species dissociated into their component ions in aqueous solution. For acetic acid, it's important again to remember that it is not one of our strong acids. And as such, I'm not going to disassociate that acetic acid when I write it in ionic equation, because again, the equilibrium of its dissociation lies to the left. That is, most of these species are going to exist in the molecular form CH3CO2H rather than dissociated before the reaction begins. So don't disassociate the weak species in your ionic equation. Sodium hydroxide, however, is a strong base, as we saw, so I'm going to go ahead and disassociate that into Na positive ions and OH negative ions. And now on the product side, my sodium acetate, again, is an alkali metal salt, and as such, I'm going to disassociate that into Na positive ions and the acetate ion CH3CO2 negative. And again, my molecular species water is going to remain as H2O undisassociated. And you'll notice here that I don't have as many spectator ions present because the acetic acid, again, is not disassociated on the left side of my equation. The only spectator ion that I'm seeing here right now is that sodium ion. The sodium ion shows up on both sides of my equation. And as such, I'm going to go ahead and cancel that out as a spectator ion on both sides, which yields now my net ionic equation of acetic acid, CH3CO2H, my molecular species, plus the hydroxide ion, OH negative, forms the acetate anion, that is CH3CO2 negative, plus the water H2O. So again, it's really important that you pay attention to what species are strong and what species are weak, because that's going to change how you write those species as their dissociations will be different, and it's going to change your net ionic equations as a result. Now, as we all remember and know and love from last year, one of the primary skills that we will be looking at in terms of your understanding of acid-base reactions is a titration. Recall that a titration is an analytical chemistry process in which we will slowly add one species of known concentration to another species of unknown concentration, and we can do some stoichiometric calculations to determine the concentration of an unknown species present within our system. A couple of quick vocab words for you here. When doing a titration, we refer to the acid or base of known molarity, which generally gets placed in the burette, not always, but usually. We call that the titrant. And the substance of unknown concentration, or the otherwise known as the solution being analyzed, we refer to that one as the analyte. So the titrant is the thing we know about the concentration. The analyte is the thing we are studying that we do not know its concentration. And generally what we're looking for when doing a titration is what we refer to as the equivalence point of that titration. A couple of synonyms for equivalence point you'll see used interchangeably. End point is another name for it, or also the stoichiometric point might be used as well. All of those terms generally refer to the point at which we've added exactly enough titrant to our analyte so that we perfectly react with the amount of analyte present in a stoichiometric ratio. The equivalence point is usually determined either with a pH meter quantitatively, determining when the solution changes from an acid to a base, for instance, or it might be determined visually with the use of an acid-base indicator. One of the popular ones we used last year was the indicator called phenolphthalein. Again, that phenolphthalein is an acid-base indicator which changes color from colorless in acidic solutions to color of kind of pinkish magenta in basic solutions. So again, generally these acid-base titrations really come down to nothing more than a stoichiometry problem. And we've given you here kind of a generic pathway that often gets followed in doing titration problems here, where we'll start off, let's say, with a known concentration base. That is, we're using a base as the titrant here. We'll start off by using the volume of the base, which can be measured out of a burette. And then we'll convert the volume of base, as long as we know its concentration, using molarity as a conversion factor into some number of moles of the base. And then if we know the stoichiometric ratio at which the base dissociates, since it is a base of known identity, we can convert from moles of the base into moles of the hydroxide ion present in the base. And then we make use of the fact that within a strong acid, strong base titration, the moles of base can be converted into moles of acid, recognizing that the strong acid and strong base titration will have a net ionic equation of H positive plus OH negative reacts to form water. That is a 1-to-1 molar ratio between those species as they react. And then we can kind of work our way backwards to get out of this mess. Once we know moles of hydrogen ion which have reacted, we then can convert into moles of the acid that must have been present if we know the formula of the acid we're dealing with. And then we could convert into whatever else we want to convert into, like the volume of the acid if we know its molarity, or we can convert into the mass of the acid if we're dealing with a solid acid as well. So that's just kind of a generic flow chart that we will use. But again, use your discretion. You guys know how to set up monorails to get from where you want to start to where you want to end up. It's all about canceling out your units properly. So with that kind of generic guideline here, let's take a look at some examples. So for our first example problem here involving titrations, this question is going to ask us here, what volume of a 0.100 molar solution of hydrochloric acid is needed to completely neutralize 25 milliliters of 0.350 molar sodium hydroxide? And obviously, because this is a stoichiometry problem, the very first thing we want to deal with here is a chemical equation. Happily for us, this is the one we looked at on our previous example slide here. So we know that hydrochloric acid, HCl, reacts to sodium hydroxide, NaOH, to produce salt, NaCl, and water, H2O. And we've got happy 1-to-1 molar ratios of all species involved in this reaction. So with that in mind, the place where people tend to have difficulty on stoichiometry problems is where to start. We've got 3 different given pieces of information here. We've got a molarity of our acid, a volume of our base, and a molarity of the base. And so people tend to stumble about which of those you want to start with. And I would suggest to you that there's really only one logical starting place. I don't want to start with a molarity because a molarity is fundamentally a ratio. That's a conversion factor. It allows me to convert between moles of solute and liter of solution. And the other thing that would kind of give me a hint here is that I've been given both a volume and a molarity of the base, and the whole idea behind stoichiometry is to use molar ratios. So it would seem logical then to start with my volume of the base because I know its molarity. I can't start with the volume of the acid because I don't know what it is, which means I can't convert from a volume into moles of my acid. So we're going to go ahead and start then with 25 milliliters of my NaOH solution. And we'll follow a pathway that's going to become very familiar to you here. We're going to convert from milliliters into liters. There are 1,000 milliliters in 1 liter. And our monorail is now set up and going. Monorail. In 1 liter, we've got 0.350 moles of sodium hydroxide dissolved. That is, again, my molarity, moles per liter we see there. And next step, we can use our mole ratio. 1 mole of sodium hydroxide reacts to 1 mole of hydrochloric acid. So now I have moles of my hydrochloric acid. Now I can get from moles back into liters. That is a ratio of moles to liters, which is a molarity. So on the bottom now, to cancel out my units properly, 0.100 mole of hydrochloric acid is dissolved in 1 liter of my solution. And to keep things tidy here, because I was given units of milliliters initially, I might as well go back to milliliters again. There is in 1 liter, 1,000 milliliters of my hydrochloric acid. And I'm going to go ahead here and quickly cancel out my units. Milliliters of the sodium hydroxide cancels with milliliters of the sodium hydroxide. Liters cancel with liters. Moles of my base cancel with moles of my base. Moles of the acid cancel with moles of the acid. Liters of HCl cancels with liters of HCl. I'm left with milliliters. Multiply across the top and divide by the bottom here, and I get an answer here of 87.5 milliliters of hydrochloric acid. Now stop for a moment to make sure that answer makes logical sense. I notice here that my base is more concentrated than my acid, which would logically mean then I will need a larger volume of my lower concentration acid in order to get the same number of moles as present in the higher concentration base species present there. So that answer checks out. I'm happy with it, and we can move on. So that last problem was kind of an introductory level titration problem here. Let's move on to something that's a little bit trickier here, kind of more AP level thinking involving a new species that you're not too familiar with. We're going to be dealing this time with a solid acid. Now, all of the acids you've dealt with thus far have been aqueous solutions of acids. This one, potassium hydrogen phthalate, is going to be one we're going to use in lab sometimes in order to standardize solutions of sodium hydroxide. So this process is going to be a familiar one from a lab we're going to do in a little bit. Potassium hydrogen phthalate is an ionic compound. We abbreviate it KHP, but be careful there, it doesn't actually have any phosphorus in it. The P stands for the phthalate anion there, which is C8H4O4 2 negative. Now, before I do any of my actual problem right here, let's just think about what that potassium hydrogen phthalate is likely to do in solution before we get too in depth here. First thing I noticed there is that this is a alkali metal compound. And as we are familiar, all alkali metal compounds are soluble in aqueous solution, which implies, therefore, when we dissolve our 1.3009 grams of potassium hydrogen phthalate, the first thing I should expect to see here is a dissociation of that soluble solid into potassium ions, K positive, and the hydrogen phthalate ion, that is HC8H4O4 1 negative. Now notice there that I've written that one H off by itself there rather than including it with the rest of the hydrogens in the formula. And the reason why is that that particular hydrogen is an acidic hydrogen. That is, it is a hydrogen which can be donated to other species in chemical reactions. Now, that being said, once I see that hydrogen phthalate ion has a hydrogen that can be donated, I could then write a reaction in which the hydrogen phthalate ion, HC8H4O4 1 negative, reacts to my hydroxide ion from my sodium hydroxide, OH negative, and in doing so, the hydrogen phthalate would donate the H positive to the OH negative, forming water, and the phthalate ion, C8H4O4 2 negative. So now I see acid-base behavior in that Bronsted-Lowry transfer of the proton from the acid, the hydrogen phthalate ion, to the base, the hydroxide ion. So now I've got some stoichiometric relationships here, and I can start dealing with my stoichiometry. That really is the hard part of this problem. From here on out, this is really just a stoichiometry problem. So I'm told in this problem, I've got my mass of the potassium hydrogen phthalate, and I've been given here a volume of sodium hydroxide needed to reach the endpoint. And we're asking you here, what is the concentration of the sodium hydroxide? Now, as it turns out, this is a really important question to ask because making sodium hydroxide solutions of known concentration is actually a little bit trickier than you might imagine initially. It seems like it should be just as easy as dissolving some solid NaOH into a solution and making some calculations, but the real problem is sodium hydroxide in the solid state is a hygroscopic substance, which means it tends to absorb water from the atmosphere. And because it does that, that means that it's really not all NaOH you're massing out when you're making your solution initially. Some of that mass is actually already made up of water, which means if I give you a solution of sodium hydroxide and I tell you it's 0.1 molar, well, that's 0.1-ish molar, and we need to really do some actual calculations to figure out what its true concentration is. So this is the process we call standardization. And usually we use that solid acid, potassium hydrogen phthalate, for this process because it is very much not hygroscopic. That is, it doesn't absorb water really at all. So I can use the molar relationships involved in this reaction to kind of work my way backwards. So here is my pathway. I'm not going to start again with the volume of the base because I don't know anything else about my base. I am instead going to start my monorail, with my 1.3009 grams of my KHP. I'm going to abbreviate it KHP to save space here. And I'm going to do that because I know the formula of KHP and therefore I can convert from grams to moles. I've already gone through earlier and made a calculation of the molar mass of potassium hydrogen phthalate, which goes down here. That is 204.2212 grams of the KHP is equivalent to 1 mole of the KHP. And now that I'm in units of moles, everything else here should look pretty familiar. From my balanced chemical equation, I see that 1 mole of KHP dissociates to make 1 mole of the hydrogen phthalate ion, HP negative. That is, again, the mole ratio from my dissociation equation. And then from my acid-base neutralization reaction, I see here that 1 mole of the HP negative ion, that is the hydrogen phthalate ion, reacts to 1 mole of my sodium hydroxide, or 1 mole of the OH negative ion, really. And then because 1 mole of hydroxide is formed from 1 mole of the sodium hydroxide, I can therefore figure out how many moles of NaOH must have been present in my solution. And I can go through here and quickly cancel out my units. We see grams of the KHP cancel with grams of KHP, moles of KHP cancel with moles of KHP, moles of the hydrogen phthalate ion cancel out, moles of the hydroxide ion cancel out, and I'm left then with moles of my sodium hydroxide in the end. And I go through and make my calculation with, it looks like 4 sig figs here to me. It's no 5 sig figs, sorry. We get 0.006371 moles of our sodium hydroxide. And from here on out, this is just easy cleanup. Now that I have moles of sodium hydroxide to find my concentration, a molarity, I'm just going to go ahead and divide that number of moles, 0.006701, by our volume of our sodium hydroxide solution, which was in liters here I'm converting, 0.04120 liters. I can make a division, and this comes out as a 0.1546 molar solution of sodium hydroxide. So you'll see that by this process, I can determine to a high degree of accuracy the concentration of a solution of sodium hydroxide, which gets me away from the whole problem of dealing with the hygroscopic nature of that species, its ability to absorb water out of the atmosphere before I make my solutions in the first place. So that's a good lab skill, and we'll practice that in the lab later on. All right, another AP level acid-base reaction problem we would expect to see here with some trickier stoichiometry. In this particular problem, we're telling you here an example number 5, a 0.3518 gram sample of industrial effluent, which is essentially just leftover industrial chemicals, industrial waste basically, contains benzoic acid and a variety of other inert compounds, and that's dissolved in water. It requires 10.59 milliliters of that 0.1546 molar NaOH solution, which we standardized in our previous problem, to reach the endpoint of this titration. And I'm going to ask you here to calculate the mass percent of benzoic acid in that original sample. So fundamentally here, what we're really looking for is what mass of benzoic acid is in this mixture, and then can I find the mass percent? So essentially this is an analytical chemistry technique. Now, thinking about this here, this is another problem again where some stoichiometry is going to be required, which means we do need, again, a balanced chemical equation. Have a look at the formula for benzoic acid there, that is C6H5CO2H, and recognize that just like the KHP here, we've got one H which is written off by itself. We write it that way because, again, this is the acidic hydrogen present in benzoic acid. So benzoic acid is a monoprotic acid, and as such, I can easily now write a molecular equation here describing the reaction between our benzoic acid, C6H5CO2H, and sodium hydroxide, NaOH. If I donate that proton from the benzoic acid to the sodium hydroxide, I end up with H2O, which is water, and then sodium benzoate, which is NaC6H5CO2. So again, 1-to-1 molar ratios here, everything's friendly in terms of that stoichiometry. And don't be scared by some of these species. They look different from a lot of the easy acids you've dealt with, but again, if you understand the relationship between an acid and a base, writing these equations is relatively friendly. Now that being said, this problem from that point on really kind of tells me where to go, because again, I've got lots of different data. I've got a mass of my effluent sample. I've got a volume and a molarity of the sodium hydroxide. I'm not going to start with a mass of my industrial effluent because that stuff has a mixture of other components in it, which means I can't convert from grams into moles because it's not all benzoic acid. So instead, just like before, I'm going to start my monorail off with my volume of the base NaOH. So 10.59 milliliters of NaOH solution. And familiar pathway now, 1,000 milliliters is equivalent to 1 liter. 1 liter of my base contains dissolved 0.1546 moles, as we determined on our previous example here. That again is my molarity, moles per liter of my base. And then, looking at my balanced equation we wrote there, 1 mole of my NaOH reacts to 1 mole of my benzoic acid, C6H5CO2H. And I've previously gone through here and made a calculation now to convert from moles into grams of benzoic acid. I just need a molar mass. So 1 mole of my benzoic acid, previously calculated, has a mass of 122.12134 grams. And watching our units canceling out here, milliliters of NaOH cancel with milliliters of NaOH, liters cancel with liters, moles of the base cancel, moles of the benzoic acid cancels, and I'm left just with grams of benzoic acid. And I go through and make my calculation, and it comes out as 0.1999 grams of benzoic acid reacted in that process. And again, if I'm finding a mass percent, all it is the mass of the component we're looking at as a ratio to the mass of the sample as a whole, expressed as a percentage. So I'll divide my 1999 grams of my benzoic acid by the entire sample mass of 0.3518 grams, multiply that by 100, and I come up with an answer here of 56.83% benzoic acid. So again, kind of clever analytical chemistry tool here. You can imagine would have a variety of different processes, from everything as simple as measuring out how much of a dangerous pollutant might be present in some sort of waste sample, to even doing some sort of mining calculations to figure out something about, like, say, the metal content of a solution which had been dissolved from some mine waste. So yeah, there's a bunch of different ways we can apply this in the real world. And we'll move on with one final example of acid-base chemistry here. So for our last example problem in this particular set of notes here, we're going to look at example 6. This is going to ask me here, we're mixing together now an acid and a base. So we're mixing 28 milliliters of 0.250 molar nitric acid, HNO3, and 53 milliliters of 0.320 molar KOH. So we mix those two things in a reaction, and we'd expect to see here an acid-base neutralization to occur. The question is going to ask me, what is the concentration of excess hydrogen ion or hydroxide ion which is present in my final solution? And the easiest approach to this problem I would recognize here is to start by going back to our knowledge of acids and bases as to what's strong and what's weak. HNO3 itself is a strong acid, KOH is a strong base, which means rather than dealing with those molecular species here, I think it's going to be easier now to deal simply with the net ionic equation for a strong acid, strong base neutralization, which we saw earlier is always H positive plus OH negative reacts to form water H2O. So I'm going to save myself some time by skipping straight to the end right there. With that being said, if I know that is going to be my net ionic equation, all that I really need to do to solve this problem is to figure out how many moles of hydrogen ion are going to form from the dissociation of my strong acid. Likewise, how many moles of hydroxide ion will form from the dissociation of my strong base. And then to recognize that because those two ions react together in a 1-to-1 molar ratio, I could simply subtract one from the other to figure out whichever one is in excess. So that's pretty much as easy as this problem is going to get. I'll then have excess moles of whichever species is present in excess, and I can divide by the volume of the solution to figure out the molarity. So let's go through that process now. So starting off, number 1, with our nitric acid, HNO3. I'm going to set up a monorail. And again, not going to start with the molarity because that's the conversion factor between moles and liters. I'm instead going to start off with my volume, 28.0 milliliters of HNO3. And this is going to be a very familiar pathway by the end of this lecture here. Milliliters to liters, there are 1,000 milliliters in 1 liter. 1 liter of my acid contains dissolved 0.250 moles of HNO3. That is, again, moles per liter, my molarity. And then, because this is a monoprotic acid, 1 mole of HNO3 dissociates to produce 1 mole of hydrogen ion H positive. Quickly cancel out my units there, milliliters with milliliters, liters with liters, moles of the nitric acid cancel, and I get moles of hydrogen ion as my final answer. And multiplying out here, I get 0.00700 moles of H positive ion are present from the dissociation of this acid before any reaction occurs. We can now do the exact same process for our base. We have got now 53 milliliters of our KOH and another monorail. Same pathway here. 1,000 milliliters is equivalent to 1 liter. 1 liter of my base KOH contains dissolved 0.320 moles of KOH. And again, that is my molarity, my moles per liter of my base. And because this is, again, a strong base, I know that 1 mole of KOH will dissociate into 1 mole of OH negative anions. Again, cancel out my units, milliliters with milliliters, liters and liters, moles of KOH cancel, and I'm left with moles of hydroxide ion. And I get now 0.0170 moles of hydroxide ion were present as that base dissociated. And comparing now my moles of base to moles of acid, it's apparent that I've got significantly more base, OH negative, present in my solution than the acid H positive that was present there. So all that remains then to find the excess, again, recognizing that from my net ionic equation of H positive plus OH negative reacts to form water, those two ions react together in a 1-to-1 molar ratio. I'm simply going to subtract, recognizing that this reaction goes to completion, to figure out how much is in excess. So if I've got 0.0170 moles of my hydroxide ion base, and I use up 0.00700 moles of that as it reacts to the acid, that's going to leave me with, 0.00996, which rounds to sig figs as 0.0100 moles of hydroxide ion present in excess here. And again, be very, very careful here about your language. This was not asking me for moles of excess ion. It was asking me for the molarity of the excess ion. And as long as we assume here that the volumes of these acids and bases are additive, which is a relatively safe assumption at low concentrations here, we're going to go ahead and then find my molarity strictly by the definition of molarity, which is moles per liter. So I've got 0.0100 moles of my hydroxide ion base. And I'm going to divide that by my total volume of solution. I can real quick add up there, 53 milliliters and 28 milliliters gives me, 81 milliliters. Convert that into liters so I can do a molarity calculation, which is 0.0810 liters. And I divide then and get a final molarity here of the excess hydroxide ion present of 0.123 molar hydroxide ion present after that neutralization reaction goes to completion. So there you have it. Again, these acid-base problems for the stoichiometry, often the actual monorail is the easy part. Sometimes on the AP level questions, it's really figuring out what the reaction is that you're dealing with in the first place that can be the tricky part to deal with, especially when we start using those weird solid acids or unfamiliar organic acids that you've never seen before. But again, stoichiometry is just stoichiometry, nothing scarier there. So thank you for watching our lecture here. I hope you enjoyed.